Hello, good day. Today we want to design base. So we're just going to talk about the most important things that happen when you're designing a base. So I'm just looking for a point where to start explaining. Okay, which is here. What we want to design is a base, the one that you saw right at the start. Okay, for us to do that, we need to find out that what is the design load divided by the area, that is the area where the base is the area at the bottom of the base. Okay, now once we do that, we come up with a pressure. That pressure has to be less than the one that the structure can carry, which is called the bearing capacity of the soil. Now what we use for this one is usually we use what is called a limited to do this check. We need serviceability limit state. This is when we use 0.1 of the GK and the QK. Okay, now when we are calculating for the pressure that is going to come from the bottom there, we're going to use an ultimate limit state, which is 1.4 GK times 1.6 QK. Okay, so what we are designing is a pad here. Now the first thing that we need to do is to look for an example. I think this one is a good example for us to start. Okay, now what we need to do here is we have a column that is 0.4 meters. It's a square column. Okay, it is carrying this much load and it is carrying this much live load. Okay, now we have a soil bearing capacity of this much. Now the thing is, these forces are going to act on top here. They're going to affect this part. Then this, if the pressure is exceeds this value at this point, this is going to sink and the structure is going to fail. Now how do you ensure that the first check is okay? Okay, the first thing we need to do, let me just do this. We need to assume a force for this thing here. We know that concrete is a density of 24. Now okay, now what we need to do is we need to assume a depth here. Let's assume 0.5. then let's assume that, okay, let me just do this, 24 multiplied by 0.5 meters, which is the depth. Then we want to multiply that one by, let's say, 2,9 multiplied by 2,9. Okay, we'll come up with a with an assumed load here of about 100. So the load that we are going to come up with, we are going to add this assumption, which is about 100 kilonewtons. This is just an assumption. It could be wrong, it could be right. We have to see as we go through the example. Okay, now we have this one, which is 1050. We're going to add this one with the dead load which we have, which is about 100. Then we are going to add the live load, which is about 300. Okay, so we've got 1450. This is the force that is coming from the column here. Okay, so if we have 1450, we want to divide. Okay, let me just use a square root like this. Okay, here we have a force of 1450 like that. Then from that force we need to come up with an area. So the soil bearing capacity is 160, which is this one. If we divide this two, we come up with an area, the area for the base. So by looking for the square root, we are actually assuming that this one is going to be a square, so it's not going to be a big problem. Let's find out how much it's going to be. It's going to be 2.9. okay, for the sake of errors and all that stuff, it will be a safe bet to use 3 meters for the sides of the from here to here. Okay, so if we are going to use that much, now we want to calculate the moment. Okay, let me just move along here and see what they've done. Assuming that the footing is a weight of this one, okay, this one is a bit more than what I was assuming, okay, so they added that to the dead load and came up with this dead load. Now they calculated for the serviceability load, which is the 1 GK multiplied. In other words, you are not going to add any partial safety factor, so you're going to multiply this one times that, and then you're going to add. Then they came up with this one. It's going to be a bit higher than the one that I came up with. Okay, now the plan area is going to be that force here, which is this amount here, divided by the bearing capacity. They came up with this number, so we need a square root of this number. So we're going to say square root of 8,7 equals, okay, let's see how far it was. It's 2.94. okay, then they assumed 3 meters square, which was 9, which is exactly what I was assuming. Now we want to calculate the self weight of the thing itself, okay, because now we have an area. Okay, now we want to calculate the area. That area we multiply it by the height, which is, in this case, they assumed 0.6. Then they came up with a number that was less than their original assumption, which is okay. Now what they then did, they calculated the total ultimate load. Okay, by total ultimate load we are multiplying with the partial safety factor. In this case, the load, as you can see here, they added this one and came up with this, which is 1150. That's what I got. I'm going to multiply it, since it's the dead load, by 1.4. Then I'm going to add 1.6 multiplied by 300, which is the live load. Then I'm going to come with 2090. Okay, let me see. Now if we have 2090 here, then they came up with this number. Okay, so the number that I came up with is the force, which is this one, 2090. Let me just stick to my guns here. It's 2090. We will come up with the very same thing at the end of the day. Then we divide it by the area, which is about 9 meters. Then we are going to come up with the bearing capacity of 232.2 kilonewtons per square meter. Okay, so now if we want to calculate the maximum moment at the face of this column here, what we need to do is we need to take this as the point where moments are going to be. This is the fulcrum or the pivot. Okay, so this pressure, which is this one in this case, multiplied by this force. Let me just do this. I said 20.2, okay, which was the force. We are going to multiply it by the distance, which is 1.3. okay, then we are going to multiply it by this distance. We came up with the total load. Then we are going to multiply it by this distance divided by 2, which is half that distance where it's acting. Okay, so we want to come up with the moment. This is why we have PS, which is this first value. Then we've got L, which is 1.3 squared. That's 1.3 times 1.3 divided by 2. This is the formula that I was just driving out for you. It's going to give us a pressure of 196.2 kilonewtons. That is the moment that the slab is going to suffer from. Okay, from that we are going to remove the concrete cover and the center or the reinforcement of 1 bar here, which is going to be 600 minus 50, which is the concrete cover. If you remember, there's a table actually that talks about the kind of concrete covers that we can have in the case that the thing is is affected by corrosion. We have to use the worst case scenario, which is about 50 or 40 depending with the grade of concrete. So in this case they decided to use 50, so we're going to do that, and we are assuming that these bars are going to be 20 millimeters. So if we subtract 20, we'll be right at the middle there. Then we came up with this value. Okay, from that point now we are going to calculate the maximum moment that this thing can carry. Okay, this is the moment that we have. So the moment that you calculate from this point, as you can see, this is the number that they came up with. It's far bigger than this moment here, so the reinforcement is enough. Okay, but the biggest problem now is not the moment. Let me just finish up. Once you have that value, you calculate the K value, which is the moment divided by FCU times BD. You come up with this value. Then you use that value to calculate the Z value, which is the lever arm. Now, before you continue here, you need to check that before you multiply with the D value, that this number, the number that is multiplied by the D, is less than 0.95 D. If it exceeds, in this case it exceeds, you'll be forced to stick to this value. You multiply this value with the D, then you come up with the maximum lever arm, which is this much. Okay, now they used that one to calculate the area of steel, moment divided by 0. Now it's 0.95 FYZ, which is you multiply with this one, the Fy is the strength of steel. You come up with an area of steel here per meter. Since this is being calculated per meter, you check if it is you check for the minimum area of steel, which is this one. So this is valid, it's a valid thing. Okay, you check from your tables, you find out that this is 20 millimeter bars, like they assumed at 300 millimeter spacing, will give you this much reinforcement, which is greater than this number here. Now, once that has been done, you need to calculate. I think I'm going to end here. Let me just end here, then maybe tomorrow we'll talk about the shear. Thank you for your time.